Hello and welcome to Video 4 in my OpenGL series. I apologize for how long it took to come up with this one since I did the last one, but when I did my last set of videos I was talking about how I was trying to learn modern GL, and conceptually I think I picked it up pretty quick, but the details were kind of hard to pick up. As always, I'm going to give a disclaimer right now. I'm not an expert at this. This really isn't much of a tutorial. It's more of me showing the things I've learned, and I hope it will help other people who are trying to learn the same things I am move forward in their own projects and such. So that being said, I'm going to go ahead and get started. And this is the video I made, or this is from the video I made last, number 3, where I made a simple little square using old style GL. And by old style, I'm using the old fixed function pipeline components. So you got your GL begin, your GL end. Your data is actually fed one vertex, one color at a time. So this guy sets the state. This is the color that's going to be applied to all vertexes that follow, and that's how you do it. And it's slow. There's a lot more CPU involved, and really the whole purpose of the graphics card is to try and handle as much on the graphics card as humanly possible. And I think that's going to make more sense, that statement, as we move forward. Another thing, you notice you have like the GL ortho, the GL matrix mode and the load identity. All of these helpers for keeping track of the matrices are also not part of the modern OpenGL. One of the things we have to do is handle all the matrices, all the math, pretty much ourselves, except for the GL mathematics library. Again, I think that's going to become, hopefully that will be understood by the time I'm done. So I'm going to break this video up into 3 parts. I've actually tried to make it twice so far, and each time when I was trying to put something together I forgot something, or I didn't explain something. I didn't feel I explained something very well. So that experience has taught me this is probably going to take about an hour and a half. And another thing, this will be the first time I've ever used editing software to try and put my video together. When I was trying to put these together, I noticed that sometimes the mic is a little close to my mouth and you can hear me breathing, and it can be very off-putting. I'm going to do my best about that, so if I screw up, and apologize ahead of time. So moving forward, I'm going to go ahead and bring up a picture of the graphics pipeline so I can kind of explain what's going on. Okay, and here's a simplified graphics pipeline. We're missing the bottom part, which is the graphics buffer, and that's where the screen is actually put to the image is put to the screen. But the only parts that I'm really going to focus on in this set of videos is going to be the Vertex Array. This is the data. The Vertex shader. That's a shader program written in GLSL. We're going to get into that. And the fragment shader. The other things that sit in between here I'm still learning about myself, and everything after that's pretty much handled in the background. So the way this works, and this has always worked, is you push your data in either with the GL begin or with the GL list, just your data. It goes through the Vertex shader, and the Vertex shader applies the matrix math that's been handled by the GL matrix modes, and then it gets fed through here, and then the fragment shader comes in at the very end and applies the color based on the data that was fed in here. Now this hasn't changed between new and old. The only thing that's changed is before these shaders were fixed function. So whenever you were changing the states, when you were enabling things, when you were setting values, you were actually setting the way that these shaders modified and worked with this data. The nice thing about the modern GL is you can write your own shaders, so your shaders can be much more efficient. Like the old ones, they had to be able to handle lighting, texture mapping, etc. So For example, for the demonstration I'm about to give, we are going to be taking a bitmap image and we are going to be writing a vertex shader to use the vertex data and the color data to put that to the screen. So let me get started then. Okay, so here we have an empty project, and I've already set this up as such in my second and third videos. The only difference is I am including a library I put together myself, this file format library. And really for this portion, I'm not going to go into detail on this too much. I'm kind of making the assumption that the people watching this already have knowledge of arrays, files. I'm going to go into detail on the way the data is laid out in the array. But if anybody wants to have more information on this, be happy to give it out. But at the end of the day, any library for reading any kind of image where you can take the RGB data and stick it into an array is usable. So that's the only difference in my environment. Actually, I'm going to say this also. Instead of setting my include directory in the GLM subfolder here, I decided to go ahead and set the directory back to the root. So when I do my includes, I'm actually going to have to put the GLM on there. I don't know if there's anything particularly advantageous or disadvantageous about that. I just liked the look of it. But anyway, so if you're unfamiliar with how to set up the environment, you can go watch my second video on the setup. So the difference between modern and sorry, one quick second. I actually pre-wrote this program so I know it's going to work. The first time I wrote it, I was kind of using my notes, and it didn't end very well, which is why I've started over. So we're going to go ahead and start the same way we did before. Modern GL and old style GL both use glue. They use GLFW. So we need our glue. And something else while I'm thinking about it. In one of my previous videos, I said if you were going to use the glue DLL library, you needed to put a define in there and make a definition for GLEW underscore DLL. I don't know where I got that from. I remember I was having a problem and I thought that was the solution, but while I was working on this project I realized I'd forgotten I'd done it, and it seemed to work fine. So I apologize to anybody I might have led astray on that one. I could have sworn I'd read that in a Stack Overflow stream, so that is spurious information and I do apologize. So got my glue, got my GLFW3. Gonna go ahead and put in IO stream for the error stream. That's what I've been using the most of. And I'm going to include my GLM. Now, as I stated, we are going to be responsible for handling our own matrix math, where the GLM, at least for me, is invaluable. It's already got all of the types all set up. It's got a whole bunch of helper functions that'll do the math for you. Very, very helpful. So GTX transform.hpp, and I'm going to go ahead, and while I'm going forward, I'm going to be inducing some of the errors I came across, because I know one of the problems sometimes I have with some tutorials is they always do everything perfectly and it always works, and when I try and modify that code to make it do what I want it to do, there are weird errors, and of course you can go to Stack Overflow and you can ask somebody, but sometimes you just don't want to wait on that. So just to be helpful, I'm going to show some of the errors I did, and hopefully that'll be helpful. So this is my own personal include for reading BMPs. I'm trying to improve my C skills, or my C++ skills. When I got into programming initially, I was doing ANSI C. So sometimes some of the way I do things are kind of an amalgam between ANSI C and C++. And so writing the BMP reader was me trying to get better with C++. Okay, and we're going to be including the vector. For those of you also from a ANSI background and unfamiliar with C++, this is a collection class that's part of the C++ standard library. I believe this was introduced with C++ 98. Vector is very cool for storing array type information. It offers you a very stable way to store your data and work with it, and you don't have to worry about managing the memory space. Alright, and you know what? I'm going to put this, just for the sake of organization, I'm going to put this up here. I'm going to put in IO manip, although I don't think we're going to use it in this one. I remember when I was trying to debug some stuff, it was nice to be able to format the output when I had to look at lists and the like. Hopefully we shouldn't have any problems, as I have already done this. Now I'm going to be breaking this up into 3 videos, and the first part is going to be about building up your data. So you saw the graphics pipeline. The first thing, everything starts with the data. You push the data to the graphics card, so the CPU has to do as little work as is humanly possible. Alright, so initially we're going to start off exactly the same way we did with our last couple of programs. Initializing GLFW. And I am an atrocious speller. Sometimes at work I get code reviews and they are kind enough to point out my misspelling in my comments. Don't mistake the humor for pride. I'm not happy about that, but I'm trying to get better. W. I know I've already done all this, so, but sometimes I think when I'm watching somebody else's tutorial, sometimes when they type it out, it makes me feel like I can follow along better. So. Alright. And this is just our error callback, so if there is any failure inside of GLFW, this will be called. It'll give us a hopefully intelligent error so that we can tell and quickly troubleshoot what's happened. It's kind of funny, in the last video I was a little bit lax in my error handling, error checking. It bit me a couple of times. I'm actually going to make it a point to show some of those errors I ran into, because I can see them being pretty common occurrences, and they're those slight things that can drive somebody nuts. And as I said, I'm trying to help people not be going nuts. Now, this is the first thing I'm going to mention. One of the big problems I had was I was not paying very close attention to the version of the API that I was using. So in one of my previous videos, I think I was using version 3.1, and my attitude was, well, heck, I just went and did some research and they're up to version 4.5, so why not kick it up to the latest version they have? And one, not all graphics cards can handle the higher versions. In fact, I came across a comment in Stack Overflow that most people like to keep it to version 3. I believe he said it was 3.2, because there is not a modern graphics card that can't handle that. I'm going to go for 4.0, simply because I'm trying to learn some of the later stuff. I figure by the time I do anything even remotely useful with this, 4 will be hopefully not too archaic. GLFW set callback. Why is that not happy? Oh well. I'm going to ignore it until it becomes a problem. So if you are having issues, sometimes it can be you have the wrong version stored. Like the versioning changes the behavior sometimes of how the buffers interact with each other, some of the requirements or expectations. So be sure that when you select a version that you have the documentation on hand to reference things, because sometimes things that work in previous versions no longer work after that. A good example would be the Vertex Array, or pardon me, the it's the Vertex Array object, the VAO. In the later versions, the VAO has become much more important in the operation of the graphics card, and we will see that as part of the data building session. So create window, and we're going to go ahead and just make a 512 by 512 window. I'm going to call this Modern GL. Why not? Put the version. And then this is for getting extended information about the monitor, extended hardware information. And really and truly, this should be the same as what we put in. So we expect this to be 512 by 512, but just for the sake of doing it and confirming it. Oops. Size. So pointer, address of. Alright, so that should give us our window and our width and our height. Alright, so now we need to make that context current. And because OpenGL, and this is something that I've just actually, hold on. Something I've noticed that I believe this is because it's so state driven. The order in which you do things can sometimes cause some really odd things to happen. Let's see, it's supposed to be frame buffer. There we go. And so, for example, at some point I had forgotten to make the context current, and when I tried to do things like call glue, it was not locking on to the context correctly. Now, but it wasn't overtly, it wasn't giving me anything useful that I could link to. I had forgotten to create a context. So, and from what I understand, I did a little research into the glue experimental. That's mostly for backwards compatibility on older machines. One thing I read kind of implied to me that this was only important on Mac machines, but I'm going to go ahead and do it here anyway, just for the fun of it. Oops. Alright, so now we've initialized our glue. Alright, so at this point we have done everything necessary to create a OpenGL context. I'm going to copy this over for some code I'm looking right here. Alright, so now at this point we've done everything to open up a GL context, and we've called glue, so all of our function pointers will be pointed to the appropriate locations. So, data. In this case, I'm going to be grabbing data from BMP files. So I'm going to go ahead and I'm going to create a function to give me to open the BMPs and turn them into OpenGL buffers. And I'm going to go ahead and call it image VAO because what we'll be creating is Vertex Array objects. And I'm going to go ahead and give it a const char for the file. This will be the BMP we're using. And I want to keep track of how many points are actually going to be created based on the image. You can get some odd things happening. And I want to return a glue init, and I'll explain that here in just a second. So the first thing we're going to do is load up our image. And as I stated, as long as you can put this image to a array, I think you should have no trouble doing what we're doing here. So my personal function that I wrote, it returns an array of structures that are RGB, that are RGB byte components. And then that way we can iterate through them and use them to build up our data array. Now, so as soon as we get this back, we're going to want some place to put it to. As I said, a vector works really well for this. Now, though this GL is modern, a lot of it is still kind of based on old NCC style conventions. So it wants to have a void pointer array. So that's where vector's really nice, because it can I'm not going to say emulate, but you can get a pointer to it and it will act as an old NCC style array. So now we've got our image with our array of data, and we've got our place to put the data to. Now I'm going to go ahead and take that point count, which is passed by reference, and set it to 0, because that needs to be, that's kind of important when we actually go to do our rendering, is we know exactly how much data is in the array. And I'm going to create this indice here to keep track of where we are in the bitmap. So we're going to go ahead and iterate through. Let's see. That's going to be Y, because this is where we're going to go. The bitmaps are going to be laid out in rows with stacked columns. So we want to go equal I height plus Y. Now, interesting thing here, BMPs are kind of, from my point of view, they're laid out backwards. The data starts at the bottom row and works its way up as you move forward. Now, I did a little research on this because I thought this was a little odd. It turns out a long time ago, when the BMP was first being conceived by the IBM guys, at least I believe that's what I was reading gave me the impression that they were doing it for OS2. There was kind of a little bit of a discussion on this, because the hardware guys they think of Origin as being in the upper left-hand side of the screen, with Y ascending as you go down and X ascending as you go right. Whereas the programmers who were doing the BMP were more thinking natural Cartesian coordinate system, where Y is ascending going up and X is ascending going right. So the natural Cartesian coordinate people, the mathematic purists, won out. So the first row is considered line 0, and as you proceed in the file, it's assumed that you're going upwards. So this actually works out well here, because we're starting at 0, we're going upwards, so the OpenGL coordinate system actually works in our favor, at least in mine for this case. So we're going to be doing row by row. Internally, we're going to be doing column by column. Alright. And as I said, the images are made out of, I'll call it O because this is a structured object. It's going to be, so now that one pixel is going to have 3 components that are bytes, R, G, and B. Now, the images I'm personally using, the background is white. So I'm going to go ahead and say if the background is white, we don't want to process it. So I'm going to go ahead and say 0. Oops. I'm going to go ahead and say if it is white, skip to the next one. And then that way we get a transparent background. Alright, so if, oops, sorry, forgot how to type for a split second. So if we get to this point, we know we have a actual pixel color that we want to make a point out of. So we're going to use we're going to go ahead and start and put our X and Y there. So these will be the coordinates of our 2D point. Now, at the end of the day, our coordinate system is going to be a 512 by 512 screen, but we're going to have, if you go to the far left of the screen, it's going to be, or the window, far left of the window is going to be minus 25, the far right is going to be positive 25. So doing these X and Y values, there's going to have to be some scaling done. And before, what I would have done is I would have done it at this point so that the data was already pre-scaled. But I hope I'm going to demonstrate that you can get the graphics card to do the math work for you, and I think it's better because that's what the graphics card really does well, is these mathematical operations en masse. So right now we're just going to leave it so the coordinates are going to be 0, 1, 0, 2, 9, 4, and so on and so forth. Now, since we're putting these all into a single array, you are by no means required to have contiguous data types. I think this just makes it easier. You can just put in their structures, and the only requirement is that they be consistent. But I like doing this because it just makes it easier to work with, and for demonstration purposes it makes it a lot easier to show. So we are going to be packing in the data in first the coordinates, and then the associated color that goes with the vertexes we create. Vertices, pardon me. In fact, I just realized we want these to be now, this will probably be done implicitly by the compiler, but just for the sake of doing it the right way. So we now have a contiguous, or we're going to have a contiguous array of GLFloats. Now this part right here, intellectually to me it should be RGB. I believe that is the order in which it is giving them to me in the BMP. That's how it was listed. But when I did my final test of the software, everything came out blue. And for the life of me, I can't figure out why. I'm going to go ahead and just do this BGR. I don't know if this is because I'm doing something wrong, or OpenGL just likes doing things in BGR format. But order is important here. Luckily, if you screw this one up, everything just looks blue. Alright, and since we've gone through here, we want to go ahead and increment the point count. And so when we come through this, we should have ourselves a fully populated array where we have 2 GLFloats that represent our X and Y coordinates, and 3 GLFloats that represent the associated color with those coordinate points. So now we need to go ahead and make a vertex array object and a corresponding vertex buffer object. Now, in one of my previous videos, actually, I just realized I never made a video. I'm going to say when I was doing a previous project that was along these exact same lines, all I made was a buffer object. And I think it was partially because I was working in an older version of the OpenGL API, at least the 4.0, and I get the impression the later versions want a vertex array object. Now, there's an upside to this, though. Actually, I may be getting ahead of myself. Let me go ahead. Alright, so we're going to make a vertex array name. And when they say name in OpenGL, they typically turn out to be integers, which to me would be more like a reference or an ID, but they call them names. This is apparently a very old convention back to the beginning of OpenGL, so this might actually be like another old ANSI throwback. So whenever we say name, we typically mean a GL unsigned integer, or in some cases a GL integer. And that is a reference to an object or a buffer of some sort on the graphics card. So let's see. So buffer name. Alright. So the VAO. The VAO is a holder of information about the data in the buffer. Now, the graphics card gets these blobs of data and stores them as buffers, but it doesn't initially know how to make use of it. For example, here we've stuck our X and Y and our BGR, but we're not limited to that. We could stick anything we want in here. We could stick like lighting locations, self-illumination. We could stick normal information, anything we want in any format we want. But when it does get to the graphics card, that's just going to be a blob of useless information. But the vertex array object is where we associate the metadata that describes what's in the buffer. That way, when we get to the shader, that information is usable. So we're going to go ahead and generate a vertex array name. Arrays, and this command is made for making batches, so we're going to go ahead and just say this is an array of 1. And then so the card is going to give us an unused name, and then we're going to bind that name. So this array will be the current one being used. So I'm just going to go ahead and copy this, be a little lazy. So right now that is the current one on the card. We have bound it. I like putting a tab right here so I can say everything that happens hereafter is associated with this Vertex Array object. So actually, yeah, I'm not going to do that. Alright, so now we're going to generate our buffer. So this is where the actual data that we collected up at the top is going to be stored to the card. And we pretty much do the exact same name. We generate a name and put it to this as an array of 1. So this is going to be an integer to misspelled. Very misspelled. So this is going to become the name of the buffer object that holds this data. And again, we go ahead and we bind the buffer. And there are a multitude of buffers that can be associated with this Vertex Array object. Now, from what I understand, the GL array buffer isn't actually bound specifically to this Vertex Array. We do have to create and bind the things in this order. And I've done some reading on it. To me, it was a little convoluted. The nice thing is the Vertex Array object is pretty much all you need to keep track of here when you get to the rendering portion. So that's why we're only going to be returning, I'm going to go ahead and do this now. We are only going to be returning this guy because he is the reference we're going to need when we want to actually draw our stuff. Alright, so we bound the buffer while we have the Vertex Array name bound. So we're going to go ahead and push our buffer data into the card. So we're pushing this into the GL array buffer because that is the one that is currently bound to our new buffer name. Now we need the size, and this is the memory size, not the number of GLFloats, but the actual size of the array, which is why I've got this up here. Okay, and then we need this to be, as I said, old style C array, so the vector will return the appropriate pointer that it can be read. And then we need to tell it what kind of data it is. Is it going to be dynamic? Is it going to be static? And I get the impression this is one of those things that when we tell this data is never going to change, that's going to allow the graphics cards to do a little bit of optimization. That's an assumption on my part, but given how a lot of this stuff seems to be, the reasoning behind all of the layout and the conventions seems to be for speed. So that's a guess on my part. So now we need to associate how the data needs to be read once it gets to the shader. Now this will probably make a little more sense when we write our shaders. So the first parameter, I'm going to call them parameters. So the first parameters we're going to pass to our shaders is the positions. So we're going to enable it because we need the first position, the first layout to be active. And then this command is what we're going to use to describe what the data looks like. So it's going to be the first, I'm going to call it parameter. This is going to be layout 0. And we're going to have two elements here because we've got the X and the Y value. And their size is GLFloat. And we'll put GL false here. This is for whether or not to normalize it. And I highly recommend, there is a gentleman by the name of Jamie King who's got a really great set of OpenGL tutorials. Hell, just tutorials on every computer science topic you could possibly think of. And he goes into a little more detail over some of this stuff. Now, he said this modifies your data, so we don't want it to modify our data, because we got our data just the way we want it. Alright, so GLFloat, GLFalse, and then we're going to do what's called the stride. And what this is this is telling telling the graphics card where is the next data relative to our first data. And since we've got 1, 2, 3, 4, 5 GL floats per vertex, we tell it that this is the offset from the beginning to the next one. So it'll be XY, BGR, and then XY. Hope that made sense. Alright, and then this is the initial position for the first. And I like doing static cast. This is the initial position for this piece of data. Did I spell that? Oh, pointer. So this, as I said, as you can see, this command will tell the graphics card how to interpret our buffer information. So the next one is going to be our BGR data. And again, one. From what I understand, you can put up to 16 attribute arrays per this. We're only going to be needing 2 because we're only pushing in this data. But when you're thinking about what you need to do with your program, try and make the graphics card do as much as you possibly can. Try and get the graphics card to do the work. I actually found myself saying that the other day. There was a project I'm working on. I might give a little talk about it at the end of this. Actually, this one's 3. Anyway, I need to keep my mind on where we are. So this is going to be our BGR values. They're all GL floats. And we do not want it to modify our data. Alright, so this is going to be the next stride. Now, from here to the next XY is going to be going through 1, 2, 3, 4, 5 floats. This is going to be no different because this is going to be going through 1, 2, 3, 4, 5 floats to get to the next BGR. So this is no different between the two of them. So I'm just going to go ahead and copy and paste it because I'm lazy. But the last one, this particular attribute does not start at the beginning of the buffer data. It actually starts 2 in. So, but again, so we need, and this is actual memory size difference. So times 2, and then this will indicate the first position of the BGR data. So this is all we've got for here. So we've created our vertex name, we bound it, we put the data in, we've told it how the data needs to be interpreted, and I believe we're done. We're just going to go ahead and do a bind buffer. And set this to 0, and then that way the graphics card is now not bound to anything. It's usually a pretty good idea to go ahead and release these resources when you're done with them. I actually had a odd thing happen a while back where I was doing some experiments with texture mapping, and I had GL textures enabled. And I didn't think to disable them when I moved to the next portion of my program, and again, everything turned blue. And I tried switching the RGB and the BGR, but there was always this blue tint to things. Eventually, when I was taking out different portions, trying to diagnose why it was doing this, taking out all the texture mapping code made it work. And I found that if I just disabled the textures when I was done with it, it wouldn't happen. So this is a cautionary tale. Always clean up your resources. Anyway, so this should be fine. I'm going to go ahead and try and build it to make sure that there's no compiler errors anywhere. And there is. But it looked like I just misspelled something. Oh, here we go. That's why it was mad. So, alright, let's try that again. Alright. Build. Alright, I forgot I had to do it this way. So, as I said, throw back to old ANSI. Alright, so now we've got our function built right here. I'm going to go ahead and bind the buffer objects. Now, first I'm going to make a little structured object whose sole job is going to be associating the vertex array names. I'll call this, actually, let's call this object. And we're going to need the name and the number of points associated with each name. Alright, and then I'm going to go ahead and create an array . Now, my particular demonstration, I'm going to be using 3 separate images, so I can give a little VAOs. So give a little demonstration of some animation. So VAO S. Actually, take out the S. This is a silly thing, but so we're going to have this populated by create image. And I got the, you can see I've got the bitmaps right here, so that indicates they're in the same folder as my project. And I'm going to also, so this is passed by reference, so that will populate those points for me. Alright. So that's going to give me a VAO for objects 1, 2, and 3. I'm going to say this real quick. I actually saw a couple of Stack Overflow comments where people were pushing multiple images into, or multiple data sets into a single buffer, and then just changing the indice from where the data was being read, so you can get that same animation effect, and you only have one buffer on the card, so whatever overhead there is from switching between one buffer and another, you eliminate. But I think this is good because this just, to me, makes it easier to conceptualize. Alright, so I'm going to end this video right here. just for the sake of time. I think I'm only allowed 30 so minutes per video. I don't know if that's true or not, but it makes it easier to make anyway. So thank you, and look forward to comments or suggestions on how I can do better. Have a good evening. Thank you for your time.